Okay, content questions, guys. This week, I think is just a lot of review. I mean, I can do like a review of the review, give you like the Cliff Notes version, but I don't know if you guys have anything. If you have anything on last week's quiz, we can do that on the problem set. I am still grading it, but the way that I grade it is I grade like one question on everybody's. So most of you have like over half of it annotated right now, even though you don't have a grade. So at any point you can go in and kind of look to see how you're doing. But for sure before the exam on Monday, right? Our exam is on Monday. You're going to want to look at, or I want you to look at how you did and compare it to the answer key. A few folks are getting their configurations wrong. Chapter 5, like on the surface, doesn't seem like there's a lot of material in there, but a lot of people do struggle with trying to see stuff in 3 dimensions. And, you know, especially like meso compounds, if you have to rotate it to try to see the plane of symmetry, and there was one like that, tend to be difficult if you're not really good at visualizing in that way. Some people are just naturals at seeing flat things in 2-3 dimensions, but most aren't. So if you're one of those people, please practice that. The exam isn't like, it's only on chapter 4 and 5 and then 6, but there's not much in 6. Like there'll be very little bit from chapter 6 on there. So basically the questions that were on the quiz and the problems that they're going to show up again. I haven't graded your video problem from last week yet, and I'm probably honestly not going to get to it until, I don't know, this weekend at the best. I'm really behind in grading my labs, and I need to spend some time getting caught up in that class because I'm really behind. And I always like do your stuff first, and I should probably be fair to my other classes. Questions?
Can you go over mechanisms and types of mechanisms?
Yeah, for sure. Let me get my iPad up here. As always, it takes me forever. I think I can do that. I swear I like do this ahead of time and everything's fine because I like test it out. And now like my screen mirroring software, the little thing that spins is just sitting there spinning. Do I want to close the other application? Sure. Oh, it wants me to update it. It's not going to get updated now. Technology. I guess this would be the one advantage of being in a classroom doing the content for me anyway, is I don't have to mess with this. Okay, I think I'm in business. Okay. It wanted me to install an update, which I didn't do, but I had to like, anyway, you guys don't care. So I guess just mechanisms in general. Mechanisms are really what we've been doing. I just haven't called them that. So all of those curved arrows where you're identifying like nucleophiles and electrophiles and drawing arrows, those are mechanisms. So a mechanism shows every single step of the reaction. So it's going to show all of our intermediates, that sort of thing. On your video problem this week, I give like both the reaction and the mechanism so you can kind of see the difference. So if like the reaction itself, I went from A to B, the mechanism could be A could form C, and then C could form D, and then D could form B, and our net is just this, but all this stuff is happening in the middle. So whenever we draw a mechanism, we're showing all that stuff. We're not just showing the net equation. So mechanisms are going to show every step of our reaction. And you would have done that part of the mechanism in 152. So in the kinetics chapter, you would have been given individual steps. And then remember, you had to like identify intermediates, cancel those out, identify catalysts, cancel those out, and add them together. So that was essentially a mechanism. What we're adding to it in this class is those curved arrows. We're going to show how the bonds are forming and breaking. So it shows every step of the reaction. It shows all electron movements. So we're going to use our curved arrows. It's going to show all intermediates. We have it. We don't always have intermediates, but if there is one, we're going to show it. So it shows all intermediates. And if you remember either from the video or from 152, an intermediate is something that I make in one step and then use up in a subsequent step. So it's produced in one step and consumed in a subsequent step. It doesn't have to be directly after it, which is why we're saying subsequent instead of next, but a step that comes after the one that you're making it, it's going to be used up. So it's something you're going to make first. So it's going to be a product first and then a reactant. That's how I would have described it in 152. If there's, sometimes it shows transition states. Sometimes. I will always tell you if I want to see the transition state as part of the mechanism. So in chapter 7, you're going to learn essentially just 2 different reactions. One of them I want to see the transition state for, and I'm generally incredibly clear. It's really hard to miss it. And the other one I don't. So kind of the rule of thumb is that if it doesn't have an intermediate, I want to see the transition state. If it has an intermediate, then don't worry about the transition state. But again, I'll be really clear as to when I want to see that or not. So it shows transition states sometimes. And these were our highest energy. I'm going to say form. It's more of a complex is kind of the better word for it. I'll explain here in a minute. It's the one that has partially formed and partially broken bonds. If you haven't watched the videos yet, the second to last one is on energy diagrams. So that's this where we would plot energy over our reaction. I'm sure you've seen these a gazillion times. So you start it with reactants, you go up in energy, and then you come down to products. This part up here is my transition state. So that's the highest energy state. Long as I'm here, the energy difference then between my reactants, which is where we're starting, and this transition state was my activation energy. So the amount of energy you have to put into it. This energy diagram that I just drew doesn't have an intermediate. If it had an intermediate, it would dip down. So something that has an intermediate is actually going to have 2 transition states because it's going to have 2 steps. So I'm going to go up, I'm going to dip down, I'm going to come back up, and then I'm going to go down again. So this would be my reactants, this would be my intermediate, and then my products, and then I have 2 transition states. So when I go from reactants to intermediates, I have a state where my bonds are partially formed and partially broken. And then when I go from my intermediate to my products, I have another state where those bonds are partially formed and partially broken. And then you're actually going to have 2 activation energies. Because we need to put energy into going from reactants to intermediate, and then we also need to put energy into going from my intermediate to my product. Notice that that intermediate is still pretty high in energy. It's higher in energy than the reactants and the products. Remember, an intermediate is something that we're going to make and then use it up right away. It doesn't have to be the next step, but it's going to be used up, right? We're not going to keep it. The reason for that is it's generally high in energy. It's unstable. It's not our product, right? We want our product to be stable. Okay, this is taking me, sorry, for your types of mechanisms, and I'm doing the entire chapter. So mechanisms, every step, all electron movement, intermediates, which is going to be this one. So this would be a 2-step reaction, this one that I have an intermediate. Sometimes transition states, those were our highest energy states. We could draw an energy diagram where I have 3 steps. If I have 3 steps, I'm going to have 2 intermediates, and then I'm going to have 3 transition states. So some types of mechanisms, there's 3 common types. One of them being like way, way more common. Like it's probably better to say there's like 1 common type and then 2 others. Like it's really that extreme. But types of mechanisms. And the first one are the ones that we've been doing, and those are polar mechanisms. So those are the ones where you have something that's electron rich, you have something else that's electron poor, and our arrows go from our electron rich to our electron poor site. So this is between nucleophiles and electrophiles. Right, and we draw our curved arrows from our electron source to that electron receptor. So all those curved arrows I've been having you draw, which you're doing again this week in your video problem. So polar mechanisms, I can do an example, but I'm going to list the other ones. Maybe we should put it here too. This had, I talked about different ways that bonds can break and form. So heterolytic and heterogenic. Lytic for breaking, because you're lysing it, and then genic is to make, genesis is to make something. So genic is forming. So heterolytic means you're breaking it unsymmetrically, and then heterogenic means you're forming it unsymmetrically. By that, when we say unsymmetrically, it means one of the 2 atoms is supplying both of the electrons if you're making it. So this example here would be heterogenic, right? The nucleophile is supplying both of those electrons to my electrophile, right? We're ending up forming a bond between these 2. And these electrons in the bond are both coming from nucleophile. So it's not like each one's contributing so unsymmetrical. If I was to break that bond, both of the electrons are going on to one of them. So again, unsymmetrical. I'm not going to use those terms a whole lot, but you should be familiar with them. Radical ones, these ones are just, people usually struggle with them, but it's only because we don't do them that much. Like if you were to do it a lot, then it probably would not be so weird. But it looks weird. We're not used to radicals. So radical, that's not how you spell radical. Radical mechanisms. And what we're doing with these is we're actually just moving like single electrons. So it has homolytic and homogenic bond breaking and forming. So this means it's symmetrical. And the easiest way is to just show you this is unsymmetrical. So unsymmetrical, 1 atom gets both electrons. Symmetrical, each atom gets 1 electron. So if I wanted to break this bond between the 2 chlorines, so we're going to do a lytic version, we're breaking. Remember that line is 2 electrons, right? If I was to draw the Lewis dot structure, 2 dots. And what's going to happen is 1 electron is going to go to each chlorine. And the arrows that we draw, we can do an arrow review, only gets 1 barb on it because we're moving 1 electron. So if we go look at the arrow for my polar ones up here, right? I had 2 barbs on it, like a regular arrow, because I'm moving 2 electrons. This one just gets 1 barb because I'm just moving 1 electron. So radical mechanisms will always have, they're called fishhook arrows. We'll always have fishhook arrows because it looks like a little fishhook, I guess. And then when I do that, I actually end up with 2 radicals, right? If I look at this one, each one of those chlorines got 1 of those electrons. So it has radical intermediates. A radical is just an atom with a lone electron. outside of this chapter, all of the mechanisms that you're going to be responsible for are going to be polar mechanisms. In 236, you do a couple radical ones. And then in this chapter, like I'll kind of, like if I give you, and we can do this today if you want, if I give you like reactants and products, you have to draw the arrows, or if I draw the arrows, you have to draw the reactants and products, that sort of thing. But you're not going to have to, I'm not just going to give you a reaction and say draw the complete mechanism for a radical one this semester. So radical intermediate, sorry. And feel free to interrupt me at any point, guys, if you have questions. By guys, I mean gals too, sorry. Just interrupt, speak. And then the third one is pericyclic. And again, this is one where you're not going to be responsible for one this semester, other than like this chapter. In 236, you do them. I know it sounds kind of weird that we're doing stuff now that you're going to be doing in 236, but it's the same textbook. It's really like just one class. Like you do the first half of the book now, and then you do the second half later. So this chapter is for the whole entire text, which is 236 also. So pericyclic. And kind of the hallmark to these is they're going to have a cyclic transition state. Remember I said a transition state is where I have partially formed and partially broken bonds. So it's going to have that, but in a circle. So peri means like around, and then cyclic means it's cyclic. So around the circle, you're going to have a transition state. You are moving two electrons. It's just not really polar because I don't think of it as, you don't really have a nucleophile and an electrophile. It's more almost, I don't want to say that. I was going to say almost resonance-like, but it's not. It's just, you don't really have an electron rich and electron poor. We do have sources and receptors because they're drawing arrows, but it's just, it's different. Let's just do one. Sorry guys. I want to do a polar one first because then I can show you, because I think it's easier and you've been working on it. So you can kind of, I'll draw a transition state and then I'll do a pericyclic one so you can look at the difference. I think it's easier sometimes if you compare and contrast. So I want to do something different than what I did in the video. I'm just looking at my pile of notes here to see if there's something I want to do. Not, I'll just make something up, but I don't know. Let's do, whoa. So this is a polar one. So, and again, this is just really what we've been doing. So I have a polar bond, right, between oxygen and hydrogen, right? Oxygen's more electronegative. It has a positive charge, but remember, formal charge is a function of the number of lone pairs and bonds it has. My partial charges is a function of its electronegativity. So something can have partial charges and still have a formal charge that's the opposite. So don't let that throw you. And then I have some lone pairs on this oxygen on my ketone. So what I'm going to do is I'm just going to grab onto that hydrogen, and then those electrons are going to go into oxygen. And I am going to draw the transition state just so you can see what it looks like. So my transition state, essentially what I'm going to do is I'm going to have a dotted line every place I'm putting an arrow. So this oxygen is going to be forming a bond to that hydrogen. So I'm going to draw a dotted line to hydrogen because that bond is partially formed. And then I'm breaking the bond between hydrogen and oxygen. So because that bond is partially broken, I'm going to draw a dotted line. And then everything else is still the same. And then to designate a transition state, you usually put brackets around it. And then this is called a double dagger symbol. I've also heard it called as like a telephone pole, but there really aren't telephone poles anymore. It's kind of old timey, but this would be my transition state. And again, I will always tell you when I want to see them. But I'm forming this bond, so it's partially formed, so it's dotted. I'm breaking this bond, it's partially broken, so it's dotted. So your transition state will always have those dotted things in it. And then my product from this, and then water. And this is just one step, but I just wanted to draw a transition state so you can kind of compare and contrast. But it's what we've been doing. So if you're hoping this would go away, I think I told you at the time that it wasn't. It's totally not. From chapter 7 through the end of the semester, we're going to be drawing mechanisms like this. So just kind of part of a polar mechanism. My pericyclic one, and there's only 2 types, so I keep doing that. I'm doing a very similar one to what we did. It's probably the exact same one. So what this is, it's normally I would draw it like this. In the video I did, and then I changed it. So I'm just putting it in, it's called the S-cis conformation. So I'm just rotating that single bond and then tipping it sideways. And then I have an alkene. So just 2 carbons with a double bond between them. And then what I'm going to do is I'm going to kind of make a circle. So these pi electrons are going to grab onto this carbon. That carbon would have too many bonds. So then these electrons are going to come up here, which would give this carbon right here that I just put the dot on too many electrons. So then those are going to come over here. And that's happening all at one time. I'm going to come back to that. We should write that here. We could say it's concerted. Concerted just means it's all happening at the same time. So it's just one step. It's a concerted rearrangement of electrons. So at the same time, I have pi electrons grabbing onto a carbon. That carbon has too many, so those are moving. And then another carbon has too many, so those are going out and grabbing the other one. So when I draw my transition state for this, again, transition states, I'm going to have a dotted line every place I'm forming and breaking a bond. So this pi bond I'm breaking, so I'm going to have a dotted line there. I'm forming a bond between these 2 carbons. That's what that one pink arrow is showing me. So I'm going to have a dotted line there. I'm breaking this pi bond. So I'm going to have a dotted line there. I'm forming a pi bond here. I'm breaking this upper pi bond, and then that last arrow shows that I'm forming a bond between those 2 carbons, so that's going to be dotted. And then because it's a transition state, brackets and double dagger. So I have a cyclic transition state, right? I just have dotted lines in a circle. And then my product from that, those guys are all now connected, and I have a double bond here. And again, you know, I would give you parts of it. I wouldn't just give you this and then say draw the entire thing, right? That's what you'll do in 236. Right now, I could give you the entire thing and say what type of mechanism is it, and you could tell me pericyclic. I could give you the reactants with the arrow and the product and then ask you to draw the transition state. You know, I would give you parts of it, but you do kind of have to know what's going on to fill in the missing parts. But that would be a pericyclic one. Again, still just interrupt me if you have questions. I'll do a radical one next. Okay. I'm trying to think of a good one for radical. Oh, we could do, that might be too big. So plastic, so like polyethylene, polystyrene, which is styrofoam, polypropylene, those are all radical mechanisms. That's how they make them. So we'll make a piece of polyethylene. And I'm not going to do the whole thing. We'll just do part of it. but we're going to use a catalyst. So BZ stands, this is, so benzoyl peroxide is what we start out with. It's kind of messy. So kind of because that's obnoxious to draw, the shorthand notation for it is this. So these two oxygens are representing those two oxygens, and then the BZ is this part. So it's just like, that's obnoxious to draw and I don't want to draw it all the time. Lazy person way of doing it. So those things are equivalent. So BZ isn't some mysterious atom that just I made up. It actually stands for the rest of that molecule. So that's benzoyl peroxide. So it's, the first part is we're going to end up breaking that bond, and each of those oxygens gets an electron. Notice how I'm using those fishhook arrows because each one is getting an electron, right? Both electrons aren't going to one thing, they're each getting one. And then I end up with BZO with a radical. I actually have two of those, right? And then my next step, and again, you would not have to, I was good, that's not ethylene. You would not have to do this entire mechanism on your own. Like I would give you a part of it and you would only have to like supply the arrows. It's only because I'm doing it that I'm doing the whole thing. So if you're sitting there thinking, I could never come up with this on my own, don't worry. I will give you parts. And I can kind of do an example of what I would expect after, but if you can get the whole thing, then it helps. So what I'm gonna do now is I have this radical, and electrons don't want to be by themselves. They want to have a friend, right? They want to be paired up. So if you, as long as you have a radical, it's going to go try to steal electrons from something else. So I have these pi electrons in my ethene, right? I have 2 carbons, it's an alkene. Common name is ethylene. And one of those electrons is actually going to combine with the radical electron on my BZO. So, and they're going to kind of meet out in the middle. So like, I'm sorry, this is going to, I know I'm being confusing, right? If I was doing polar, both of these electrons here are being given, right? So I can actually draw an arrow from one thing to another because it's going from one thing to another. When I'm doing bond formation, that's symmetrical, right? When I'm doing the homogenic one, I actually have to meet in the middle because BZO isn't giving the electron to my ethene molecule and ethene isn't giving the electrons to BZO. They're meeting in the middle, right? They're each giving an electron. So it looks kind of weird, but this electron is going to combine with one of these pi electrons and they're just going to kind of meet somewhere in the middle. And then my other pi electron is going to go on to that carbon. So these would be my arrows. And again, like I would either give you the product and you have to give the arrows, or I would give you the arrows and you would have to give the product. But what I get now is I have carbon, it still has its 2 hydrogen, and it's now bonded to BZO. And then my other carbon has a lone electron on it and it's 2 hydrogen. So basically I'm going to erase this pi bond. I'm going to put it as 2 dots, right? Because it is 2 dots. So one of those dots is combining with this dot, and that's this bond. And then the other one, this one here, is this one. If we wanted to do another step, I said that we're making a polymer. Put that back. Right, so we're going to keep going. Polymer is just, poly means many. So we have many of our monomer, mono means single. I have many of them hooked together. So I'm going to take many of my ethene molecules and bond them to each other. And then I have polyethylene. So I'm going to draw another one in here. Doesn't have to be sideways. But now I'm going to do the same thing. So one of those pi electrons, I got that hydrogen in the way, so I didn't leave myself much room, but we're just going to go over the hydrogen. They're going to meet somewhere in the middle. And then that other electron is going to go onto that carbon. So what I have now, you got to give yourself some room because I'm going to have 4 carbons in a row. So my first carbon with my BZO attached to it and its 2 hydrogen is bonded to a carbon with its 2 hydrogen. But then that carbon is now bonded to my next monomer. It has 2 hydrogen. The carbon that is bonded to has a radical and 2 hydrogen. And then that just keeps repeating. You would put another ethylene molecule in there. Ethene molecule is IUPAC, sorry. Ethylene is not IUPAC. And you would just repeat that last step I did over and over again until you have plastic. Of course, it's more, in practicality, more complicated than that, but that's the mechanism for it. So just to make sure everyone can see where all these are coming from. So these 2 carbons are these 2 carbons. And then these, ooh, my phone's ringing. As you can see, sorry. It shows up on my iPad when it rings. Okay. These 2 carbons are those 2 carbons. So an example of a radical mechanism. They're usually pretty obvious. Like if I was to draw a piece of this and ask you what type of mechanism it is, the only one that has radical intermediates and fishhook arrows are the radical ones. These ones, pericyclic and the polar, might be a little bit more tricky to differentiate between, but just look for this intermediate. So it's always going to have a cyclic, or not intermediate, sorry, transition state. It's always going to have a cyclic transition state. It doesn't have an intermediate. There's no intermediate in that reaction. So kind of, if you're wondering kind of what I would expect, like if I drew, I don't know, if I did CH3, CH2, this, and then this makes no sense. Change this to Cl2, diatomic chlorine. I could say supply the arrows. So I'm giving you reactants and products, and then you have to put the arrows in there. And then hopefully you would notice that there's radicals. So the arrows that you're going to use are fishhook arrows. If you use arrows with 2 barbs, you're doing it incorrectly. So I would look at this and say, okay, there's radicals. I need to draw those radical arrows. And then just do like we've always done, like look at the before and after. So initially, right, I have a carbon with a radical on it and 2 hydrogen. Over here, this carbon has a chlorine bonded to it. Here I have 2 chlorine bonded to each other, and here I have chlorine with a radical. So I'm obviously taking one of those chlorines and attaching it to that carbon, and then the other chlorine is going to be by itself. So my arrows, and again, you need fishhook ones, and they're going to meet somewhere in the middle, and then that other one's going on chlorine. I drew it down. You could have drawn it up. It doesn't matter as long as it's a fishhook arrow and it's going on to chlorine. And then that would be your answer. I could ask what type of mechanism this is. You would say radical. I don't know. It's like that sort of, what kind of bond breaking and forming does it have? Homolytic, homogenic. I might have said that backwards. The lytic is the breaking, the genic is the forming. Questions right now?
I just have one quick question about, with the benzoyl peroxide, what happens to the other radical of that, or are we just using one?
We're just, yeah, what's probably happening is it's probably, it's like, this is probably happening like twice. Like
Gotcha.
you never, yeah, you never just have one molecule, right? If we had
Mhm.
like a mole of molecules, we had 6.02 times 10 to the 23rd of them. So it's, I probably have like, I don't know, a gazillion of those, right? Something times 10 to the 23rd of them. And then I have more than that of my ethylene molecule. So it's probably just reacting with another.
While you're doing the whole, okay, just like throughout the process. All right. Thank you.
Yeah, you're welcome. That was one of my things. Like it's a really common question. Like when you get to biochem, because we're so used to like just focusing on this that we forget that we're focusing on like one molecule, but there's like that's not what you know what I mean. Like there's a gazillion of them. And then like when you get to biochem and you're looking at like metabolic processes, we forget like if we're just looking at glycolysis, we forget that like things feed in and out of glycolysis into a whole bunch of other pathways. It's really easy to not see the big picture. So, and that's why, like, and that's also one of the growing pains with organic because I just hardly ever balance stuff because I'm like, I don't know, it's doing something else. Who cares? But when you're coming from Gen Chem where like everything has to be balanced and neat and orderly, yeah, it's weird. This is why organic works for me because I'm not orderly. Other questions?
No.
So no, you guys are good with last week's stuff. I mean, I'm totally cool doing this week. I just want to make sure because you do have that test that everyone gets a chance. I am willing to do a review session. I mentioned that at the end of class last week. We can talk about when we want to do that. And you can ask those questions then and we can just focus on this week. This is the bulk of it. This and then going back up to those energy diagrams, I'll likely ask you to draw one. Parts that I didn't put on this initially are my overall energy change. So the difference between my reactants and products. Your book is calling it enthalpy. It's Gibbs free energy is probably more accurate. I would just know both and then pay attention to what I'm asking for. So if I ask for the overall energy change, it's delta G. If I'm asking for the enthalpy change, if I use the word exothermic or endothermic, it's delta H. If I use the word spontaneous or non-spontaneous, it's delta G. All of that is in that video. So if you haven't watched it, I do review it really quickly. I don't spend a lot of time on it, but I do review it. You're not actually going to be like plugging numbers into the calculator and calculating energy changes. I just want you to be able to look at this and say, okay, my products are lower in energy than my reactants, so it's spontaneous. We're going to use all of that next in chapter 7. If you are reading the text, which I hope you are, but I think it would be unrealistic for me to think that everyone is, but if you are reading the text, there is a section on bond association energy, which I have not covered, and I'm not covering it this week, so don't worry about it. You could read through it, but there won't be any test questions on it. And I think there's some kinetic stuff in there. I talk a little bit about kinetics in the video, so just know like the level of detail that I talk about in the video. Don't worry about determining if stuff is first order or second order yet. We'll do that in chapter 7. Chapter 7, we're going to have 2 mechanisms and we're going to differentiate between the two based on kinetics. So I'll review kinetics in chapter 7. So you can just skip those parts of chapter 6 for now. Other questions? Usually I go over and I kind of, it's a short chapter. I can review some of the other stuff in the last few minutes we have. Or do you guys want to just come up with a time for a review session? Do you want a review session? Last time only like 3 people came. Like I want to do it for you, but if it's like a waste of my time, I guess if 3 people come, it's not a waste of my time because I'm helping 3 people. So no
The
one
test
comes.
is on the 21st, right?
What's that?
Test is on the 21st, right?
Test is on,
I
it's
think
on
that,
Monday, whatever day that is.
Okay, never mind. I think this says something different on the, or maybe we're looking at a different class. I don't know.
Did I goof up? I want to know if I goofed up. Hang on, let me look. I'm clicking on stuff.
No, it says October 19th at
My
10
bad.
a.m.
Okay. I have it a couple places. I'm just trying to. Yeah, I got October 19th, so that'd be Monday.
My bad.
And I'm gonna do it like we did last time. Everyone said it was okay, and no one said it didn't work with them. So starting at 9:30, let's actually write this down. 8:30. Did I just say 9:30? Starting at 8:30, because then you get that extra time. Like I'll still make it, so you should be able to do it in 50 minutes. But because it's online, I know it usually takes longer, and you have to upload stuff. It's gonna be last time. There's gonna be 2 parts. So exam 2 is going to be Monday, the 19th. That's this coming Monday. So unless you come to the review session, I won't say you again before that. And I want to start at 8:30 with part 1. Nobody said last time it was a problem for them, so I'm just assuming that it's not going to be a problem for you guys again. If it is, please send me an email, let me know. But hopefully everyone can start at 8:30, because that gives you extra time. And then part 2 will be due by 10 o'clock. Because I know some people have class at 10. So just like last time, this will be on Canvas. And this will be written. You have to turn it into a PDF and then upload it to me. So you'll start part 1 at 8:30. When you're done with that, go and do part 2. And then just make sure you get it uploaded to me by 10. If you have problems, please email me. So let's do this Friday after your quiz. I'll have the Zoom session open. So if you guys want to review, we can do a review. And then I can stay maybe till about 10:30. Because you're not going to get there right at 9. You have to take your quiz first. So I can stay till about 10:30. So from whenever you get there till then. If you have class at 10, I don't want to exclude those people. So do you want to do an evening one also, like we did last time? This is where you guys get to tell me what you want. Okay, I wanted to come last one, but I got busy. I will record it again and put it there. If you can't come and you have questions, you can email them to me, and then I will cover them in the session, and then you can watch the video and get those answers. I did that last time for one person. Hopefully I did a good job of it. If I suck, Seth, please tell me.
Sorry.
That's okay.
No, you're good. Unfortunately, I won't be able to be there either because I work that day.
Okay. How late do you work till?
I work from 10:30 to 11 p.m.
Okay, yeah, I'm
So
not doing it.
12. Yeah, I was like, so it's not gonna
You'll just
happen.
have to email me your questions. Sorry.
No, you're good. I'll do that.
Okay. So do you guys want an evening session? Someone has to, either you do, you don't. If you're silent, I'm gonna assume you don't. Nick, you came to the evening one. Did you want to come again, or does the morning one work, or do you not care?
Monday or the one on Friday works because I won't be at work that Friday, so I can
Okay.
I'll probably go to both to be real, but if there is afternoon one.
Well, I'm gonna schedule one then, and if no one shows up, I'll just cancel it. So let's do another one. Session 2. I'm only gonna hang out till about 10 after, and if no one shows up by like 10 after, let's do it at, what did we do last time? 3 o'clock, or was it 2 o'clock? I don't remember. I think it was 3. Let's do 3. No one's telling me, so I'm just picking. If you want it to be a different time, now's your chance to tell me. Only then for till 4. And then if no one shows up, I'll just cancel it. Okay. So exam on Monday. Don't forget, I do want to start at 8:30. If you have a problem with that, please let me know as soon as possible. And then this Friday, that's next Monday, this Friday, after the quiz, I'll just have Zoom open. So when you're done with the quiz, feel free to jump in. The way I do the review sessions is you have to like have questions. So hopefully you've studied a little bit, you've had questions on stuff, you can come and ask them. And then I will have Zoom open at 3 o'clock if you also want to jump in. If no one does, by 3:10, I'm out of here.
Okay.
Not really out of here, I'll just work on other stuff. But okay.